have the privilege, and it'll really be terrific, of hearing from 3 explorers. And these individuals use technology to explore and try to understand remote and, to this point, inaccessible places, like other planets, our sun, and the deep recesses of the ocean. They'll each speak for 10 minutes, then I'll ask a few questions, and then I'll open it up to you. And we're going to start with David Gallo. Before we start, though, I don't know if your mics will have feedback the way mine is, but if there's something you can do about it.
We'll give it a try. That sounds good.
That would be great.
Me.
So, so Dave is an oceanographer and director of special projects at the Woods Hole Oceanographic Institution. He's a leader in undersea exploration. He's participated in explorations of the Titanic and Bismarck and the missing Air France Flight 447. He's a pioneer in using both manned submersibles and robots to clearly map our ocean worlds. Dave.
Thank you, Paula. And will someone give me an 8-minute? Let me know when 8 minutes are up so I can.
I have my trusty iPhone here.
Let her rip. Slide number 1. So you'll recognize this, I hope. It's planet Earth. It's an unusual view. So it's the Earth spun around Google Earth, and we're looking at the Pacific Ocean. This planet is covered with ocean, 70% covered with water. Average depth is about 2.5 miles. So that's a lot of water on this planet. Now I'm going to talk about 2 things. One is that this planet's hardly been explored at all. We've explored around 5%, 6%, number changes who you talk to, but it's less than 10% of this planet, because most of it's under all that water. Second part is how important it is to explore that Earth. You know, if you flatten out the Earth, this is a map by Hazen and Tharp, and I love it because it shows some of the most dramatic features of the seafloor. It's not a big blue fishbowl. When you go down to the bottom of the ocean, we find some of the most incredible features. There's a mountain range that goes around the Earth. It's like the seams of a baseball called the Mid-Ocean Ridge right here. It's 50,000 miles long. It dwarfs, there's thousands of peaks that dwarf any of the peaks around here, 4, 5, 6 times higher than any of the peaks you see here. Thousands of valleys wider and deeper than the Grand Canyon. We find underwater rivers, underwater lakes, underwater waterfalls. The greatest waterfall on Earth, we're told it's Angel Falls in Venezuela. Actually, it's between Iceland and Greenland right here, 5 times higher than Angel Falls, but it's beneath the surface of the sea. What's the problem? The problem is that the water's so deep, the ocean's so vast, it's difficult to explore. And there's a philosopher, great philosopher, Yogi Berra, and he said, you can observe a lot just by watching. And Yogi's right, but to watch so deep, to observe so deep, the cornerstone of science, you have to have technology. And we've got a bunch of technology that we use. This is a classic piece. It's the submarine, Alvin. Right now, Alvin's in the Pacific Ocean. It's just been upgraded, and it's about to embark on a new voyage of discovery. And it's been great in the past. 3 people sitting in that submarine. Being pulled out on deck, passions running high, and everyone in that submarine wondering the same thing: should I have gone to the bathroom one more time? Because it's a 10-hour day in that vehicle. But every time you get to this point, up the A-frame goes over the back of the ship, the fantail, and down into the water. This splashdown right here is an amazing moment. And no matter how many times you dive, that lovely color blue penetrating into the sphere changes you. It penetrates your very spirit. You stop hearing the sounds of the surface ship, the machinery, all that junk, and you start to hear this lovely pinging of the submarine, the pinging sound of the sonar down to the ocean and back up. The divers give you the all clear to go, and on the way you go, 3 of you alone, you're not hooked up to the surface in any way, on your way to the deep. It's a 2.5-hour journey. The first half hour you pass through that lovely color blue, from light blue to deep blue to dark blue. The rest of it, pitch black. Sun's never been there. Now, we were sure that because sun's never been there, that there'd be no life at all until, oh, I'm sorry, I forgot to mention this. A new addition to our submarine fleet. You may have seen this in the media that just a week or so ago, Jim Cameron delivered his submarine, the Deep Sea Challenger, to us. He used this to dive to the very deepest part of the ocean, the Marianas Trench, so we now have that. Oops, sorry. And also robots. Robots are playing a whole new role in ocean exploration. We're just entering that world, and here we are as one of our robots. This is by Hanu Singh, peering beneath the ice of Antarctica. So we were sure the deep ocean, being black all the time, would have no life at all. When we stop and look, we find out that there's incredible amounts of life. It's full of life, and animals that are incredibly delicate. I love this one. It's got these fishing lures on the bottom. It's got tentacles. It's got independent stomachs, a whole row of them. This one's about 8 inches long. It's got jet thrusters, a little light. Fully grown, it could be as long as this auditorium. So it could be 100 feet or more long. Animals that look like they came out of space. So, you know, it's just an amazing world. And in the past, we would tow a net through that world and try to put these animals back together again from a pile of mush after about 8 hours of towing, and mush and body parts. But now our technology is good enough that we can go there and actually look and see where they actually live, look at how they behave. When we get deeper in the sea, on top of that mountain range, we found an amazing thing. That looks like smoke coming out of the seafloor. It's actually hot water. The temperature is about 700 degrees Fahrenheit. It's horrible. It's that rotten, eggy, sulfuric smell that you get up around hot springs. And we said there could be absolutely no life. It's too deep. It's too dark. There's always earthquakes, poisonous fluids that would kill us. You couldn't get a permit to dump this in the ocean if you tried. So we were sure that we shouldn't waste time looking for animals down here until some geologist, stumbling along, looked off into the distance, and they found abundant amounts of life that you'll see in a moment here. And here we go. So here we come through the fog of the deep sea, and you'll see the life starting to come in. This is a pillar of volcanic rock. It's about twice as high as this room. Everything on there is alive. In one spot, we found 300 species of animals, 297 of them brand new, never been seen before. And all of these animals living off that hot stuff, the chemical stuff, the poison stuff that's so bad for us. So we're finding life here in diversity, the kinds of animals, and density, the number of animals, that rivals the tropical rainforest. We were dead wrong about life on Earth. The deep sea, living off chemosynthesis, not photosynthesis, is rich with life. Okay. This is a web clip that I'm going to show. In fact, I think this has aired a couple times, but I want you to show it, just so you don't think everything new and exciting is at the deep sea. This is the work of Roger Hanlon at the Marine Biological Laboratory, who's studying octopus camouflage. And there's an octopus hiding here, a big octopus, and here comes Roger. And you'll see him in a moment. Voila. Isn't it stunning, right? So that's a big animal hiding yeah, how about that? So once it's seen, once it thinks it's been seen, it scoots off into the distance, tries to bluff Roger. Roger, being smart, followed it right to its spot. And now I'm going to run it backwards. And here's the amazing thing. You watch this animal on the right, the smooth, light-skinned, big animal on the right, and it's going to turn into that crinkly stuff on the left, this algae and stuff on the left. It's hard to believe that that animal can do that. But watch it happen here in slow motion. There we go. Just amazing. So totally amazing. And Roger, if you check his website, is doing some incredible stuff. Okay. Nighttime in the darkness view of a lake. So you see the water sitting down there. Here's a better, closer look at the water, the ripples in it. That water is at the bottom of the sea. So from where you're sitting, you're looking out the window of the sub or a monitor on a robot at another body of water at the bottom of the ocean. There's lakes at the bottom of the sea. Some are pretty big. And some are pretty deep. They can be up to 300 feet deep, and they have their own ecosystems. There's animals living in that water that don't live in the ocean, animals living in the ocean that don't go in there, animals that live just along the shore, so underwater lakes. Despite all that, this is an attitude. This is from New Yorker magazine, and I don't know why I don't care about the bottom of the ocean, but I don't. And here's the deal. We're an ocean planet, okay? 7 billion people living on this planet. There's no place that you can live and not have the ocean impact you every single day, through weather patterns, climate, all that stuff. There's no place that you can live and not have an impact on the ocean, the converse, because anything you put in the air or on the ground actually eventually makes its way to the sea, and it's getting to be a crisis situation. We're finding stuff that trickles off our shorelines and the fish, even in the deepest, most middle parts of the ocean basins. You can't see humanity on that slide, and it's amazing to me. At nighttime you can, like the jellyfish in the sea. This is from WorldSat Inc., a picture of the Earth at night. So you can't see any view of humanity on this planet. We're that tiny. And yet, just like the octopus, you can't believe it could turn into that stuff. It's hard to believe that something like a virus on this planet, we've managed to change the chemistry and temperature of the oceans, and we have done that. So the ocean chemistry is changing, the temperature is changing, and it's all because of us. That's not a natural rhythm. Natural rhythms are there, but we've got our own little addition that we've made.
Dave, you have 8.
Okay? This is my last slide. And I started out by saying ocean planet, blue planet, look at all the ocean, right, when we need to explore it. One of the biggest issues we see today from the humanity point of view is how much water is there on this planet. You know, the oceans provide us with the air we breathe. Every other breath of air you take, 50% of the oxygen comes out of the sea. The food we eat, the oceans are all about that. And the water we drink, a huge amount, more than 80%, 85% of the rain, where it rains and doesn't rain, is controlled by the ocean. We decided one day to look at how much water there was on the Earth. That's the Earth on the left. That's all the water on the right, this ball right here. So if the Earth is the size of a basketball, all the water fits into a ping pong ball. That's because the oceans, yes, they're deep, 2.5 miles deep, but the oceans are thousands of miles wide, so the layer of water is thousands by 2. And the last thing I want to show you is the fresh water, which is that little speck right there. And for us to live the way we do, you have to take that little speck, put it in the right places, right time of year, in just the right amounts, or everything goes upside down. So that's it for my 10 minutes. Thank you very much.
Okay, Dave.
Sorry for racing.
So I have one question that I'm sorry I can't resist asking. So you mentioned James Cameron.
Yes.
And I know you've worked with him a lot. And I know that a year or two ago he went to the bottom of the Marianas Trench.
Yes.
Did you go with him on that?
I was not on the expedition. Okay. It was an amazingly disruptive thing he did to us, because here's a filmmaker. I mean, he's got a passion that runs as deep as he dove for the oceans. He's a very serious engineer, very serious, in a way, environmentalist, naturalist. And so that shocked us. You know, we watched from Woods Hole, we worried, we laughed, we cried, we applauded. It was an amazing thing that he did. And he did it with a team that he put together from his local community of engineers and scientists.
So that's the deepest point of the ocean, is that true?
The deepest point is 7 miles. That's the Challenger Deep in the Marianas Trench. When you see a jet with a vapor trail behind it, that's about 7 miles. So if you're in there looking down, that's as deep as the ocean gets. Average depth about 2.5.
Thank you.
Yep, thank
okay,
you.
Now we'll move on to Maria Banks,
Maria.
who's a research fellow at the Smithsonian's National Air and Space Museum. And Maria first became interested in glaciers as they sailed past the observation deck windows on the cruise ship where she was a harpist. So I'm sure there's a great story there. And now she explores glaciers and ice sheets and sand dunes and the landforms that they create on both Earth and Mars. She worked on the Phoenix Mars mission and currently works with the science teams for several spacecraft orbiting Mars, the Moon, and Mercury. Maria, would you like an 8-minute warning?
Yes, please.
Okay.
Okay. Can you hear me okay? Good. Oh, great. Okay. Well, thank you, Paula. So I'm a planetary geologist. What does that mean? That means I like to study activity, things that are happening on the surface of the Earth, as well as other planets and the Moon. To be totally honest, I want to be an astronaut. Seriously, I'd like to be an astronaut. I want to walk on the surface of Mars. But since I can't quite do that yet, as a planetary geologist, I can use data sent back from orbiting spacecraft. And I can use that data to find clues as to what has happened on the surfaces of these planets, and even better yet, what's happening now. And as Paula mentioned, as a fellow at the Smithsonian Institution's National Air and Space Museum, I've had the amazing opportunity to work on 3 active spacecraft missions currently in orbit around Mars, the Moon, and Mercury. We have the technology now to see things on the surfaces of other planets we've never seen before. And so I would like to take you on a walk on the surface of Mars through the eyes, of a high-resolution camera called HiRISE. Now, HiRISE is on a spacecraft called Mars Reconnaissance Orbiter, which is currently in orbit around Mars. Now, HiRISE is the highest resolution camera we've ever sent to another planet. As a matter of fact, it has a resolution so high that if any one of you was standing on the surface of Mars, we would be able to see you. So now the spacecraft has been in orbit since 2005. So in that amount of time, we've been able to see details, of course, that we've never seen before, and actually actual activity on the surface that we've never seen before. Things on Mars are very similar to things we see on Earth, but a little bit different. And by studying them, we can learn more about what's happening, what it's like on Mars, and also a little bit more about what it's like on our own planet Earth, too. So let's start our walk on the plains of Amazonas, where HiRISE recently captured this. This is a dust devil, and you might be familiar from them. We have them on Earth in very dry desert regions, especially in the southwest of the US. So it's basically a spinning vortex of air. It's a little bit like a tornado, except without the storm, and typically smaller in scale. Although with this one, by measuring the shadow there, we know it's about 1/2 mile in height, which is quite large. So no walk across the surface of Mars is complete until we come across one of these. This is a crater, an impact crater, formed by an object from outer space crashing into the surface of Mars. And this one's kind of special because it's a new one. We know it's new because we can go back in time now. We have enough images over time that we can look at that surface and see, okay, that crater wasn't there, now it's here, and we can pull out of that roughly when that impact happened. And it's creating this great dark pattern here because as it impacted, it blew off all the nice bright dust on the surface and exposed this dark surface underneath. And craters are also great tools because they excavate below the surface and allow us to peek at what's hidden underneath. And this crater over here in the lower corner there, you can see some white material at the bottom, and that's actually ice that was just below the surface, and we didn't actually know that it was stable there, and so that was a surprise. And if we hadn't been able to capture that, it would have sublimated away. That means going from ice form into vapor form before we even had a chance to see it. So now let's leave our walk for a moment. Let's jump into a helicopter, and we can fly into one of these craters, a much larger crater, a much older crater. And I wanted to show you these. These are some new things that we haven't quite seen before. There's these brown lineations coming down. Now we're inside the crater in our helicopter, and we're looking at the wall of the crater. So these lineations, these brown lineations, are new things we've just recently beginning to notice, and we've named them recurring slope lineae, which is science for we're not exactly sure what's forming these. But we have been able to watch them over time. This is a little animation made up of high-res images that were taken over the course of a Mars year or so, and we see that in the summer seasons, in the warm seasons, these appear and they flow on the surface, and then when it gets colder, they slowly disappear. So as I said, we're not exactly sure what's forming these, but our best guess, our best hypothesis right now is that this is very briny, salty water, and it's stable just below the surface, and it's finding cracks in the wall of the crater and flowing out temporarily when it gets warm. It finds these cracks, it's able to flow out before it evaporates and disappears. So this is really exciting. This is our best persuasive evidence yet of possibly actual flowing water on the surface of Mars. So now if we continue our walk to the north, eventually we're going to hit one of these. This is an ice sheet. Now Mars has ice caps on the north and south polar caps, just like we do on Earth. And you can see these, I wanted to show you these spectacular layers, which are created by variations in climate. They record variations in the climates on Mars over time, just like we have layers in the ice sheets on Greenland and Antarctica. And on the edges of this ice sheet, sometimes they form these really steep high cliffs, sometimes more than a mile in height, and sometimes more than 80 degrees in slope. And HiRISE captured recently, for the first time, material crashing down one of these cliffs and forming a big plume at the bottom there. So this is what we think is basically an avalanche captured for the first time on the surface of another planet. So to get your perspective, this bright stuff over here, this is carbon dioxide frost on top of the ice sheet. Then it's false color, so it looks brown, but it's really water ice with a little bit of dirt mixed in. And that's the cliff, and then that's the surface over there underneath that. And we're seeing this avalanche of material crashing over. And so this brought this area to our attention, and we now know from HiRISE that this happens often in the spring, and we've managed to capture several examples. And what we think is happening is that in the spring, the temperatures are warming, the ice is becoming less stable and avalanching down, just like we see here on Earth in the springtime. So now if we leave our ice sheet and we continue walking on Mars, eventually we're going to run into one of these crazy features. These are actually sand dunes, and they form shapes on Mars very similar to the shapes of sand dunes on Earth. For example, these long skinny ones are longitudinal dunes. And we also have these little crescent-shaped dunes, which are called Barchan dunes. And they vary nicely. The horns on these, I guess they're going this direction, they point in the direction that the wind is going, so they can tell us something about the wind on Mars. So also, we can use our understanding of dunes on Earth to kind of tell us what's happening or what happened on the surface of Mars when these formed. So if I pretend my hand here is a dune, my hand's a Barchan dune, and you're all laying on your stomachs on the ground and you're looking at it from the side. So the wind blows sand grains so that they bump and skip and hop and roll up the dune, and then they cascade down the front. And in that way, that enables the dune to move across the surface, or shall we say walk across the surface. And so we can use wind tunnels on Earth to actually, we have one in California that simulates the low atmospheric pressure on Mars, and we can use that to understand how fast that wind needs to be to get that lift and that low atmospheric pressure to actually move those sand grains. And we know that it's about 30, for regular sand grains, like sand grains we have on our beaches here, it's about 30 meters per second. That's roughly 65 miles per hour. So I just think this is kind of amazing. Just from seeing this one Barchan dune on the surface, we know a whole bunch of things about Mars. We know that there's sand grains available here, and that something's eroding to make those grains. For example, this cliff right over here is nicely showing us where it's eroding. We know that the wind is blowing. We know that it's blowing this way, and we know that when these dunes were forming, that wind, at least at times, was blowing at least 65 miles per hour. We have over 500 sand dunes on the surface of Mars, for example, one of these right here. But this posed an intriguing question. Scientists watched these dunes for decades, but we never saw them changing. We never saw them moving or new dunes forming. So what happened? We know that the conditions existed at one time for them to form and to move. So did something change on Mars? Did the climate change? Was the atmosphere once much thicker, in which case they could move under much lower velocity winds? So myself and several other scientists started to use our new high-rise camera to take a very close look at some of these sand dunes, and even individual dunes like this one in yellow right here. And only in the last couple years have we finally been able to see them moving. So these are two high-rise images that are being blinked back and forth that were taken roughly 4 Earth years apart, or that's equivalent of about 2 Mars years. And we started to see new dunes form, if you look at the white arrows. And we even started to see ripples on top of the dunes moving, if you again look at the white arrow up there. But not all of them are moving. So here's where we are. The green dots show where we have seen dunes moving. The red triangles are where they're not moving, and the blue ones, we're not exactly sure what's happening there yet. So anyway, why are some moving in some places and some not in other places? Did things shift on the surface of Mars, but only in some areas? And maybe they're moving, but we just haven't been able to detect it yet. We have global circulation models that predict for us where we think winds will be highest on the surface of Mars, but they don't match where we see the dunes moving and where we don't see them moving. So is it possible they're the ones that are moving, it's just due to these small-scale, really fast wind gusts that just aren't resolved in these global models? But if so, were there wind gusts at one time where we see dunes but they're not moving now? And what happened? What changed? What other factors might be controlling this? What does this tell us about what's changing and shifting on Mars? And likewise, what might be changing and shifting on our own planet as well? So these are some of the questions that I'm trying to answer. We have over 500 dune fields, so we need to put a lot more dots on that map. And since I can't walk on the surface of Mars just yet, I can let the dunes do the walking for me. So stay tuned, and hopefully in a couple years, I'll have some more answers for you.
Thank you, Maria. The picture, the story you're telling of Mars is a story of a planet that seems alive now. Yet I think a lot of people have a picture of Mars, but somehow it's a geologically dead or inactive planet. So which is it? What's the real story of Mars?
It's a very active planet, and that's why I wanted to show some of these things. Only with taking images over time do you capture some of these. I said a couple times high-rise accidentally captured this, got an avalanche, found a dust devil, and you know, just we're finding more and more things. I only showed you just a small portion too, that the planet is really very alive, very active, and that's something, you know, even scientists didn't realize to the degree that we do now.
So you're really changing Mars's image.
Yes.
Okay, now we'll move on to Justin Kasper, who's a lecturer in astronomy at Harvard University, as well as an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Justin is interested in the phenomena created around and in the sun's atmosphere, solar wind and solar flares, and is currently leading an international team building sensors for the NASA Solar Probe Plus, which is scheduled to make history in 2018 by being the first human-made object to enter the solar corona. Justin.
Thank you. So let's go back 150 years, late summer of 1859. And astronomers all around the world were watching the sun because something really odd was happening. A giant dark spot larger than Jupiter was slowly emerging on the surface of the sun. So people were drawing sketches of the sunspot. British astronomer named Richard Carrington every day would take a mirror and bounce an image of the sun onto a screen of paper and draw a picture of it. And one day, just as he'd finished drawing the picture, something really incredible happened. And I think it's more fun in his own words, although I'm sorry I can't do a British accent. While engaged in the forenoon of Thursday, September 1, in my customary observations of the solar spots, an appearance was witnessed which I believe to be exceedingly rare. 2 patches of intensely bright light broke out. The brilliancy was fully equal to that of direct sunlight, but within 60 seconds, it was much enfeebled. Now, what Carrington had just seen for the first time was what goes down today still is one of the largest solar flares or solar explosions in recorded history. Over the course of those 60 seconds, we estimate that an amount of power equivalent to all the energy used on Earth for 200 years was released. Now, Carrington couldn't see what happened next, but it turns out that explosion released material, flung it out into space, and just 20 hours later, speeding straight towards Earth, that material struck us. And all sorts of really wild things happened. The aurora borealis that night was seen all the way down to the Bahamas and Hawaii. People in New York reported reading the newspaper off the glow of a red sky at 2 in the morning. Sparks began to fly from telegraph poles and telegraph switches. And in fact, for the next 3 days, telegraph systems around the world, the Victorian internet, shut down. And when they started to recover, people were able to send messages, but only if they didn't plug in any power supplies. So you just have people saying, sending these messages, what's going on here? Okay, so fast forward now 150 years later, the space age, we're able to see things that Carrington couldn't see himself. We can take images using spacecraft, and we can watch the connection between solar activity and Earth. And we're able to appreciate that there's some really mysterious things going on at the sun, and that these mysterious things can have a real effect on life here on Earth. And what we're going to do, I'm going to show you some of the images and how we look at the sun and what these mysteries are. But with the same technology that lets us study the sun from afar, just 5 years from now in 2018, we're going to send this probe called Solar Probe Plus into the solar corona. So before we get to probe, let's just look at what the sun looks like. Right, so here's a recent image taken by a spacecraft near Earth of the sun, invisible light, and this is a lot like what Carrington was seeing in 1859, except for a couple little sunspots, nothing compared to what Carrington saw. The sun's a pretty uniform shade of yellow. And it's yellow because the surface of the sun is at a pretty benign temperature of about 6,000 degrees Celsius. Okay, so it looks like there's a pretty sharp transition. Right above the surface of the sun, there's nothing there. It's just deep space. So where is the sun's atmosphere? Where did this explosion that Carrington saw actually happen? And it turns out the sun's atmosphere is very hard to see in visible light because it's really dim compared to the surface of the sun itself. So how can we see it? Well, in Carrington's time, there was a little bit of a cheat. And this is a painting from actually 1571 titled Astronomers Observing an Eclipse. And what you do is, if you knew when there was going to be a solar eclipse, these rare times when the moon, which is actually the exact same size in the sky as the sun, would pass in front of the sun for just a few minutes. If you were in the right place on Earth at the right time, you could look up, the sun itself would be blocked, and as your eyes adjusted, this weird structure of rays stretching away from the sun would appear. And it reminded astronomers of a crown, so they called it the solar corona, which means crown. So let's look at a modern picture of a solar eclipse. So this image was taken by astronauts on the International Space Station in 2007, looking down on Earth just as the shadow created by the moon passed over the surface of the Earth. And now I'm going to show you a photograph taken at the exact same time by some people standing in the middle of that shadow looking up at the sun. All right, and with the sun blocked, and if you squint, you can just make out the craters on the surface of the moon there. With the sun blocked, you see this incredible structure of rays just stretching up and away from the sun. And this is the solar corona. Now, if you're on the ground, you can have a really nice camera and a big telescope, and you can take beautiful images. If you're up in space, we can't take images that are quite as good, but we can use a telescope with a special baffle that blocks the sun and look over a period of time, because these eclipses only last for 5 minutes. How static is the corona? So this is a sequence of images taken over the course of a few months. And the sun is indicated by that white circle in the center. And so what you see is the corona is not stable. It's actually jetting away from the sun in every direction. We call that the solar wind, and the solar wind flows typically at around 1 million miles an hour. And that's not all. Every now and then, like there, and there on the right, let's see, let's wait for another one. There. You have these things we call coronal mass ejections. And these are these instances where the sun decides to lift 1 billion tons of material out at maybe 3 million miles an hour. Carrington couldn't see it, but after the flare that he witnessed, one of those coronal mass ejections flew out and it was pointed straight at Earth. And that's what caused the disturbances 20 hours later. So what's powering all of this? How are we able to get this million-mile-an-hour wind, these coronal mass ejections, these solar flares? It turns out something really weird is going on in the solar corona. In order to see it, we need to look not in visible light, but in ultraviolet light. So this is a recent movie of the sun taken with a special telescope in Earth orbit that only responds to ultraviolet light. And here's what's wild. I said the surface of the sun glows yellow because it's at about 6,000 degrees. Well, you can only get light from material in these wavelengths if it's at a temperature of 1 million degrees. Now, we only realized this about 100 years ago. The surface of the sun is at 6,000 degrees. Within 50 miles, which is nothing in terms of the size of the sun, the temperature jumps up by hundreds of thousands of degrees. And that whole solar corona is at a temperature of between 1 to 10 million degrees. We do not know why that is happening. You know, on Earth, if I bring my hand near a fire, you know, a source of heat, the further away I go from the heat, the cooler my hand gets. It's very unusual that something would get hotter as you get further away from it. And this is the source of energy that powers the solar wind and these flares and these coronal mass ejections. Right, and I'll just show one more movie of a coronal mass ejection. Let's show it one more time. All right, and that structure has a very strong magnetic field in it, and that's what causes problems at Earth when it passes by. Okay, so it's been 50 years since the dawn of the space age. We have these amazing spacecraft taking these images, but we still have very fundamental questions. What's heating the corona to millions of degrees? What makes that solar wind happen? How can we predict when those coronal mass ejections are going to happen and whether they'll hit Earth? So before NASA even existed, people said, we need to build a solar probe. We need to send a spacecraft into the sun's atmosphere to collect samples of the corona and figure out how this is all happening. So this is an artist concept of the spacecraft. We're deep into our design phase right now. Our launch is planned for July of 2018. 8 minutes. And I'll just point out a couple key features here. The main thing is when we encounter the sun with the spacecraft, the sun will be 520 times brighter than it is at Earth. It'll be 20 degrees across in the sky. The front of the spacecraft will get up to about 1,300 degrees Celsius. It's going to be absorbing about 3 megawatts of sunlight. So we have a heat shield made of a special material called carbon foam, one of the best insulators that we know of. The front will be hit by all this sunlight, but the back of that heat shield will radiate less heat into the rest of the spacecraft than a single light bulb. Now, we'll launch on the biggest rocket we can get. That still doesn't give us enough speed to get close to the sun. So what will happen is 2 months after launch, the spacecraft flies just over the surface of Venus. And as we scooch over the surface of Venus, the gravity from that planet will pull on the spacecraft slightly, bending its orbit, slowing it down, and bringing it towards the sun, while we simultaneously speed Venus up slightly. No one will notice. A month after that, we'll have our first encounter with the sun. What then happens over the next 5 years is we have 6 more encounters with Venus, each time bringing us closer and closer to the sun. In total, we plan on 25 separate plunges through the solar atmosphere. Now, this is a little animation, and what will happen during an encounter is the solar panels pull back because they don't want to see the sunlight during the encounter. And the only things that are exposed are those antennas that'll measure electromagnetic waves coming from the sun, and that little periscope on the top. And that periscope is called the Solar Probe Cup. And it's an instrument we're building at the Smithsonian Institution. And it can actually survive looking straight at the sun. And its job is to scoop up the atmosphere as we fly through and measure how hot the corona is, what it's made of, how fast it's flowing. Now, you might wonder, how do we convince people that we can build something that will survive an encounter with the sun? So here are just a couple photos of one of the facilities we use on Earth. This is the largest solar furnace in the world. It's located in the Pyrenees in southern France. So it's a mountainside of mirrors that track the sun, and they bounce the sunlight on the side of that building. And here's a photo of me visiting it. And this is not a fisheye lens. The whole 7-story building is shaped like a parabolic mirror. And all that sunlight is focused into that tower. Into a vacuum chamber, we have a prototype of our instrument. All right, so if all goes well in 5 years, We'll be launching these instruments on the spacecraft, finally getting the data we need to figure out how the corona is heated, how the solar wind is created. That's not the only reason we're doing this. Let's go back to that Carrington event and ask, what would happen if the Carrington event happened today? Now, the National Academy of Sciences studied this just a few years ago, and they found that if there wasn't enough advance warning, the same magnetic fields that cause sparks on telegraph lines could decimate power distribution grids around the world. In fact, what they found, Lloyd's of London predicted $2.5 trillion worth of damage could be done just within the US, and the eastern seaboard of the US could be without power for up to a year. Okay, so for these reasons, why the solar corona is heated, and how to protect ourselves in society from these space weather events, it's time to build a solar probe to go and touch the sun.
So, Justin, what do... What's the relationship between sunspots and solar flares? And are solar flares more dangerous we're in a solar max now?
Yes.
Yes.
Yes, great questions. So, a couple things. Sunspots. Okay, so the sun's hot because there's a lot of energy being released in the center of the sun. And it's all boiling up to the surface. And you can't see it with your eye, but a sunspot is a chunk of really strong magnetic field popping out from the surface of the sun. And it stops the churning from happening, so the plasma gets cooler, and so it appears dimmer. If you look at the ultraviolet movies that I showed, you could see these bright things with lines coming out. And those were actually, each of those places were sitting above where with your own eye you'd see a sunspot. And that's where the solar flares happen. Strong magnetic fields get too close, and they just explosively cancel out. We're at solar, or approximately at solar maximum right now. So this is where you see the most flares. Historically, the most dangerous flares tend to happen just as solar activity is declining. So the next year or two should be particularly interesting.
Okay, well, we can think about that while we have to make a dangerous logistical move to move close together for the question. So we should just get up and sort of do this? Okay, wait. A few minutes of questions, and then I'm going to turn it over to you as soon as we get our mics back on. And the question that comes to mind is, we're really talking about exploration here. When I introduced these four people, I introduced them, these three, I'm sorry, as explorers. But today, exploration is different from the way it was when, for example, Shackleton went to Antarctica. We explore much more with scientific instruments and robots. So I'd like to know, do you consider it much the same? Is this exploration modern style? And do you consider yourselves explorers or scientists? And what's the difference?
Start with me.
Sure.
Well, in my case, because we're doing ocean exploration, we still have to get on ships, still have to go out onto the ocean and go. You can't do it from space because light, radio waves don't penetrate through the ocean, so we have to actually get in the water. So there's still that element of risk, and in fact, you used Shackleton as an example. We're now looking at ways to find Shackleton's ship, the Endurance, which is somewhere beneath the Antarctic ice in the Weddell Sea. And believe me, the thought of spending time on the ice of the Weddell Sea has got us worried. I mean, it's dangerous, it's risky, but we accept doing it as part of the, we'll try to minimize the risks always, but we accept that risk. But I do agree there's another side of exploration that you can do in some ways just by closing your eyes and dreaming, or by sitting at your computer or laptop or iPhone and just exploring. So I think there's more ways that you can explore these days for sure.
Right. I mean, I think in times past, exploration always implied some element of personal risk, physical risk. I don't know. What do you think, Marie?
Well, I do look at what I do as a form of exploration, but of course our ships that I use are more like spaceships now, and it doesn't really at least as a planetary scientist who's just collecting the data here, it doesn't pose much risk to me. But it's definitely a form of exploration. Sometimes we're finding new things every day, and there's still much more to be found. And just take, for example, the Messenger mission, which went to Mercury. Up until just 2008, we had only actually imaged with a spacecraft less than 50% of the planet of Mercury. And so, you know, take planet Earth, 70% of the Earth is roughly water. If we'd only imaged less than 50% of the Earth, we could have a very distorted view of what it really is. So I do see it as exploration. And I like what Dave was saying is that, you know, all of this data is available on the internet, and you can all be explorers too, and they have citizen scientist programs.
Yeah, I do get worried about the idea of the hero explorer, that because, you know, I think those days maybe have gone by a bit, although we always look for heroes. But I think you can all be heroes, and especially with young children, I always tell them, you know, don't let anyone do your exploring for you. Just because someone else has seen it before doesn't mean you won't get something totally different out of that experience. So I don't like it when we think there's only one way to explore. The one person to see the Grand Canyon, the Rocky Mountains, it's all been done. No, go explore for yourself.
Justin, it would be very risky indeed. You would go to the sun.
Yes, that's right. We thought of sending a graduate student, but it seemed like you know, it is something I really love about what I do. That, you know, there's this. Yes, I could sit in a lab and I could have an experiment, and I'd at least know, you know, every day what was going on. Here, you make a commitment for, you know, 5-7 years that you're designing the spacecraft. You're not personally taking risks except for your reputation. I think it's worth it to have an opportunity to send a probe to the sun to take that risk. But, you know, you have hundreds of scientists and engineers working as hard as they can to try and understand those risks and design a spacecraft that can survive. And I find that challenge is, you know, as exciting as the science itself. In terms of exploration, you know, one thing that amazes me, some of those really nice movies I showed you of the sun, we take 3.5 terabytes of images of the sun a day now from one spacecraft, and they're streamed online immediately in real time so people can look for solar events. And what's been happening since that spacecraft launched the last few years is we'll see something interesting happen. We start emailing, oh, you know, we should make a movie out of that, and we'll have a press release, and this is going to be fantastic. And as we're having those initial email conversations that night, you know, a friend of mine will say, hey, check it out on CNN. There was a solar eruption, because everyone's watching these data now. And I think that's fantastic. Let everyone around the world see these data as they're coming in and feel like they're participating. And then we're all exploring together.
So were any of you inspired by stories of explorers of old to go into what you're doing?
Sure. I have a nonverbal learning disability. I had a hard time reading all through school, still do. And ADD on top of that, so I'm a PhD ADD. But one book, when I was a child in grade school, captured my imagination. It was Kon-Tiki by Thor Heyerdahl, and I must have read that book 15, 20 times. And so that, more than anything else, got my attention. And then later on, 1976, an article in National Geographic magazine by Bob Ballard, Exploring the Deep, that really got me focused on the sea. Yeah.
For me, I think one of the key moments, I was interested in space as a kid, but I read a biography of Robert Goddard, who was one of the pioneers of modern rocketry. And actually, he had a writing disability he had to cope with, which, you know, made it more of a struggle for him. But he also had to cope with the fact that, like, you know, all he wants to do is build this rocket. And, you know, the New York Times writes an editorial. What a fool. Like, everyone knows a rocket couldn't possibly work in space. There's nothing for it to push against. And, you know, he had to persevere against, you know, a lot of public skepticism in order to show that what he was doing could actually work. And I definitely found that part of it very inspiring.
Really?
Definitely, you know, learning about Christopher Columbus in school and Captain Cook, and read the book Endurance, Shackleton. Just, I think you mentioned that I worked on a ship at one point. I think that was part of that. I wanted to try to be an explorer as much as I could as a musician at that point. But I was definitely inspired by the astronauts and the work that they do, and that brought my focus into space. And what are some areas that we truly, don't know sometimes anything about, and that just seemed like a great avenue for my interest.
So I have one more question, but you can raise your hands and Britta will go and hand you the mic. What do you think are the greatest unmapped frontiers? If you could do one thing or visit one place or understand one thing, what would it be?
Oddly enough, it's complicated. Mine's the relationship between humanity and the Earth's rhythms and cycles. The Earth is has been changing for 5 billion years. The face of the Earth changes, the climate changes. It's we've got highs and lows and highs and lows, and over every single scale, long-term, short-term, great distances, micro scale. It's like a symphony, 5 billion year long symphony, and then finally here comes humanity. And that's the thing I would love to understand better, is the relationship between all those rhythms and cycles, that lovely symphony, and us showing up with our pots and pans clanging around. Where do we fit into that, and how do we influence one another?
So we'll go to this question, and then I'll go back to this.
Okay, so this is just a follow-on to that, Dave. As we see CO2 being absorbed by the ocean more and more, the acidification that's occurring is very apparent at the surface. What are you seeing in the deep ocean? Is that going on there?
That's a great question. It's something we need to know, is that so much of the initial observations, the question is about ocean acidity, that the oceans absorb about 1/3 of the human-generated carbon dioxide, so we're changing the oceans from what they are normally to an acidic ocean. And that turns into carbonic acid, which makes it difficult for fish to make shells, skeletons or shells, and animals to make shells. And so we're seeing it at the surface. It's patchy, but it looks like it's global, but we don't know enough about what's going on at depth, because that means a whole different kind of tool, whole different technologies, but we're gearing up for that. It's a question of funding and getting out and doing it. It's one of the biggest crises that we're looking at right now. Anybody that's got an aquarium knows if you change the temperature and the chemistry, you're asking for trouble, and we're doing it. We're asking for trouble.
Okay, question over here. Oh.
You talked about looking at life in the deep, and it was all visual images. But today we could use things like genomics to also look at that. Do you have anything to say about that aspect of?
I'm sorry, what was the second?
Genomics, looking at the DNA.
Oh, no, sure.
Of the deep.
Yeah, no, that's being done. I'm not, I'm a geologist by training, and I'm always told I don't have a license to practice biology. But that's a real hot field, because we're thinking in some cases we're looking at biogenesis, that in those deep hot vents where we see animals clustered around water coming out of the seafloor, energy coming out of the sea, that we're looking at new life being formed there every single day, that it wasn't just 3 or 4 billion years ago, and then eventually we got to kangaroos and people. But we're looking every single day on this planet. So that's one of the hottest things going right now, no pun intended, is the genomics of the deep. Understanding how they all relate to one another.
More questions?
The climate change issue, is there any legitimacy to the notion that solar activity has caused some of the recent climate change that we've experienced?
No. We look at that. There hasn't been any clear direct indicator. Sorry. We've tried, you study, whatever you study, you always want to show people it's important for as many other applications as possible. And we've looked, and the changes in the solar intensity are just not that dramatic. And actually, one of the funny things is just because there are a lot of sunspots, like dark spots, doesn't actually mean the sun is much dimmer during those periods. Because you've got the flares going on, the amount of X-rays and UV the sun's giving off is actually maybe 100 times greater now than during solar minimum, even though there are all those sunspots. So we haven't seen any clear correlation there.
More questions?
We have a couple more minutes.
Okay. Can I finish the answers to my question? Greatest unmapped frontiers. Maria, Justin.
Well, I personally, I just enjoy trying to understand how a planet or a surface or just even a geological setting, how it happened, how it got to be the way it was, kind of like a gigantic detective story, to find all the different clues and pieces to piece together that story. And I enjoy doing that on small levels on the Earth or Mars, as I was telling you about with the sand dunes. But then also, there's such a variety in our solar system. Each of the planets are so incredibly different, and just trying to understand how that all happened, what small thing happened to set the planet on such a different course, shall we say. Anyway, that's very interesting to me.
Justin?
I guess, assuming we make it into the sun with solar probe, and we check that box, because that would make me very happy. But after that, I mean, two things come to mind. There's a satellite orbiting Jupiter called, a moon orbiting Jupiter called Europa, and it has a liquid saltwater ocean that's maybe tens of miles thick. Why have we not gone there? I want to go under the ice there and see what's going on down there. Liquid saltwater oceans.
Stick with the sun.
Yeah, stick with the sun, right? How hard could it be?
You stay out of the oceans.
And then the second thing is, just this week we learned that there are just 20 light years from here, there are 3 slightly larger than Earth-sized planets in that magic habitable zone where they could have water and support life. And I would love to be able to see what those planets look like. Is there anyone on there waving back? Are there trees? And I feel like we're getting there where we'll have the technology to be able to study the atmospheres of these other planets.
So very quickly, do you see in your students, in kids, in the general public, the spirit of exploration? Is it still alive and well, or is it flagging?
No, I see it from the urban areas to the rural areas, from the affluent to the desperate, and then we drum it out of them. So I see the twinkle in their eyes, and we try to squash it as fast as we can. That's what I feel. The way we deal with these kids, instead of encouraging curiosity and giving them the big picture, the kinds of things you just hear. Now we try. It's like if you learn tennis from someone that never played tennis, you test them on the pressure of a tennis ball, the thickness of their ball, the rigidity of the racket, everything but giving them the racket and the ball and saying, go have fun. Mm-hmm. So I think we need to change the way that we introduce.
Yeah, I mean, there's no shortage.
Thank you.
You get emails all the time from kids. That's the wonderful thing about the internet. Everyone can find your email address. Right. And you'll get 7th graders saying like, oh, I heard about your thing. Could you tell me about this? The problem is just any one person can only reach out and interact individually with one person at a time. So we really need programs to support kids who are interested in these things. I am where I am today because I saw the space shuttle on TV. I heard about Apollo. I thought it was all the Voyagers. I thought it was awesome. That made me go into the sciences. And I think it is very dangerous in the long term for this country to not have kids be interested in research and exploration.
I agree with what my colleagues have been saying. I do see tremendous excitement from people at times. They are very interested in space exploration and understanding what's happening on other planets. And I also think, though, we need programs to encourage adults too. There is a lot of focus on the children, and that's great, and I don't want to take away from that at all. But I think we also need to be engaging adults too, because your excitement shouldn't end when you grow up. It should continue on and get everyone involved.
And the adults influence the children.
And the adults influence the children, absolutely.
Thank you very much, Dave, Maria, Justin. Thank you.